Okay, welcome all. My glasses broke today, so I see a blurry haze and a little bit of an audience. Uh, Today all errors are not mine, but the glasses. Yeah? So in the grand plan for this lecture, I had said we're going to discuss image representations forever and ever, and in the end we'll talk about modeling. This was a good plan, but I got a little bit tired of image representations, so we're making an excursion to modeling now for 3 weeks or so, and then we can talk about more representations and the practical things that you can do with these. So today I want to talk about Markov random fields that have ruled supreme for the past 10 years or so. And I try to, so if Markov random fields were a political party, then I guess this would be their motto. So specify locally and model globally. This is the gist. You define only local properties, and that allows you by transitivity to get a sometimes decent, sometimes not so useful model for global properties. So in a nutshell, what is good about Markov random fields? Most of all, the convenient modeling. As you will soon see, it's sufficient to write down an energy function of just a few random variables to define your entire model. It sometimes allows for fast inference, where inference means reasoning about the most probable state of your hidden variables, and also sometimes good performance. Now actually there's just one or two variants that allow for fast inference, and people have gone to great lengths to model anything in terms of these particular variants that do allow for fast inference. And sometimes the simple model is expressive enough and sometimes not. On the bad side, generally speaking, learning is difficult. So the field is just coming to grips with finding the parameters for the potentials if the structure of the network is given, to also infer the structure itself. The problem called structure learning is harder still. So learning is difficult, and well, sometimes inference is fast, and often inference is slow. And we'll see abundant examples of such hard cases in the next 2 weeks. Today we'll talk mostly about a variant that's very inference friendly. A couple of examples of what people use Markov random fields for. Almost everything really. So segmentation into foreground or background, semantic labeling, which means you want to find out if a pixel is part of a cow or a house or a dog or a street. Then stereo matching for wide baseline images and depth estimation. Denoising, super resolution. So super resolution means taking a bad image and turning it into a higher resolution one. It's interesting in, well, for all things criminal especially. And pose estimation. And this list goes on and on. Okay, so those are kind of things you can do with MRFs. So the plan for today's lecture is I first want to define what a Markov random field is, and I want to give a few modeling details of 2 or 3 types of models, and then I want to talk at great length about continuous valued MRFs. So about the definitions. A Markov random field is a countable set of random variables which in image analysis applications are often, but not necessarily, indexed by spatial position. Now to specify an MRF, you need 3 ingredients. Firstly, you need to define what is your set of random variables. And I want to give a concrete example here. The Ising model. This is the way it's pronounced because this was a physicist who was born in Germany and then fled the Nazis to the US. And as an example here, I'm taking a particular paper from the turn of the millennium by Boykov and Jolly. And this image tells you what this particular Markov random field does. The user puts a couple of annotations. So you see there's a red dot here, and then there are blue dots in the background. And this algorithm then looks for a foreground or background labeling of each pixel, where the model encourages adjacent pixels to have the same label. And this encouragement is particularly strong in regions where the image has roughly constant brightness. And this encouragement is less strong in areas where you have a strong gradient. And you see here the kind of segmentations that you get as a function of the annotations. So here in B, the user added an extra annotation, which I hope you can see, which I guess gave the correct result here. If, however, you prefer having just the interior without this region, then you could put an extra annotation there and you would get that result and so on. So this is an example of seeded or interactive segmentation. And this needs to be, by definition, if you want this to be interactive, you need the computer to respond very quickly to any human input. And actually the model is constructed in a way that is inference friendly, so it is possible to get a very fast turnaround time. And in the bottom here you see a 3D example of how you can carve out or how you can segment out structures using a few inside-outside clicks. So in this case, the set of random variables is just the set of pixels. So this choice number 1, set of random variables, is 1 per pixel. And you will see in the textbooks and in this lecture many pictures like this. So here I'm plotting 9 pixels, And these 9 pixels are associated with 9 random variables. Let me give you another example. The Potts model, also after a physicist, and the difference between Ising and Potts will become clear only in a few minutes. I'm here referring to a paper which is about as old, so from 2001, Markov, Wechsler, and Zabi. And well, it's more of a theoretical paper really, but they also give a sample application. And it's one that you know from your exercise last week, those who did it. So you see a pair of stereo images. The images are indeed a little bit different. So for example, if you look at the shadow here, it's not quite the same between the two pictures. The images need to be rectified first, and after rectification we have so-called epipolar lines, which means the pixels on this first green line are known, if they're not occluded, to lie somewhere on this green line in the second image. And what we do now is we take a patch of this first image and we cross-correlate it with the second image. So we move it, let's say the reference position of this patch was perhaps here. So this is if I'm not shifting the patch at all. And I can now look at a couple of copies of this patch. So one version which is shifted a little bit to the left, another version which is shifted a little bit to the right. And if I just take these 3 positions, then I can only estimate 3 different depth levels. If usually you would take a couple of more positions, and you would then ask for each pixel in the image, and this is what you see here in the bottom left, you would ask for each shift which gives you the best match. So if I'm taking the green patch from the left image, should I shift it by -1, by 0, or by +1 in order to get the best match on the right image? And if I color code the best match, and if I'm using not just 3 levels, but I don't know how many these are, perhaps 10 or so, then I'm getting the image on the left-hand side, which, you know, it's not that bad, right? So it gives you, you can see that there's something closer and something further in the back, but of course it's not ground truth yet. And on the bottom is what you get if you optimize a Potts model, in which you let these estimators for the individual patches talk to each other. So the Potts model says adjacent patches prefer to have the same label here, depth, rather than a different depth. And you see that you get something which is much closer to the ground truth here. But again, so far we're only talking about the random variables. So again, the set of random variables that I'm picking here is 1 per pixel or 1 per patch. If I'm using completely overlapping patches, then it's fine to say 1 per pixel. And then I could draw the same picture that you've just seen for a 3x3 image. This is what it would look like. Okay, so we need to specify the set of random variables. And on this set of random variables, we then define an undirected hypergraph which comprises 2 sets. On the one hand, it has the set of vertices x, and on the other hand, it is hyperedges or cliques E. So for example, I could have a conflict graph where I have random variables and then these hyperedges. So the random variables, each circle is a random variable, and then I would have a hyperedge that says out of these random variables, each of which is binary, it can be on or off, only one of them is allowed to be on maximum. And similarly, out of these three random variables, only one is to be allowed on at any one time. And out of those two, only one is allowed to be on. So a forbidden solution, for example, would be to have this one on and this one on because they are here within the same hyperedge. A hyperedge is just or a hypergraph is just a generalization of a normal graph where each edge can connect more than one vertex. There is another way of representing hypergraph in terms of an ordinary graph. So if I'm using the same set of random variables here, I could also indicate such a hyperedge in terms of binary connections, where, however, where a clique or a hyperedge is defined by a completely connected subset. So all vertices, so in this representation on the right-hand side here, all vertices from the same clique must be connected. So let's go back to the examples here. So for the Ising model, it's very simple. I just have ordinary edges, no hyperedges. So these are so only adjacent pixels are connected in the graph here. It's actually the same for the Potts model. Adjacent pixels are connected. We will see later today and in the next weeks more complicated real-world examples with more complicated connection patterns. Okay, and these hyper edges are interesting because we will define a probability for this entire set of random variables that can be written as a product of terms that have in their scope only these random variables that reside within one hyperedge or within one clique. So I'm leaving a little bit of space here because in a few minutes I want to come back and talk about factor graphs. But before I do that, let me write down what I just said. A specific hypergraph represents not a single distribution, but a family of distributions. That all factorize as follows. So the joint probability of x1, x2, and so on up to n is a normalizing constant times a product over, this is meant to be a capital script C, so a product for all cliques from my set of hyperedges and then I have compatibility functions phi that depend only on the random variables within such a clique. So this would be a compatibility function on clique C. This normalizing constant, the physicists know it as partition function. And provided that the member from this family is strictly positive, which means that the probability must never become exactly zero for any combination of its arguments. So it must be non-zero. Well, and we know that probabilities are not negative, so let me write directly. It must be positive over its entire domain. So greater than 0 over its entire domain. If that is true, then it can be represented as a Gibbs measure. That's the measure associated with the Boltzmann distribution. So the probability x is now a vector. So this is the set x1 up to xn. Let me use a different E here. Okay, I'm calling this energy, even though in physics you would expect to see another constant here that represents inverse temperature or temperature. So let's say this is energy times inverse temperature. Well, and this energy can be rewritten in terms of the logarithm of this product that we had above. So I can say that the energy of a particular configuration is a sum over all cliques in this set of hyperedges. And this is called the potential on clique C. There's sometimes a little bit confusion with the terminology here. So I call this a potential and the thing up there a compatibility function. But some authors call the compatibility function the potential. So one is in the log domain and one is in the original domain. So in my terminology, potential is just minus the logarithm of such a compatibility function. Now these graphs are only interesting if they are sparse, because this sparsity induces the Markov property. So the Markov property says that if I have a subset A of all random variables, and if I condition on my entire set of vertices except for this subset, perhaps I should write this as minus A, then this is the same as conditioning on only the neighborhood of A. So delta A is now the neighborhood of my set A, and I will say what it is in a minute. Which, because it's so important, also has a name of its own. This is called the Markov blanket of a set of nodes. And these are all the nodes not in A which are in a clique with any member of A. So in formula, the set of random variables which are not in A, but which are in a clique with some variable xj which is in A. And this clique must be an element of my set of hyperedges. So xi must not be in A, thanks. So in the examples that we've discussed so far, let's say I am interested in this node here, then its Markov blanket in the blue node, then its Markov blanket is given by all the nodes which are connected. So let's say the blue one here is my set A, and the green set is the neighborhood of A. And so the probability now of this random variable taking any of its possible values only depends on what values these adjacent random variables, those in the Markov blanket, have, and it does not depend on the entire rest. So to express this in probabilities, so I can say that a subset of random variables A is conditionally independent of all other random variables given its Markov blanket. So in formula, A is, if I condition it on its neighborhood is independent of all other variables. Like that. So we've specified first our set of random variables, and then secondly a specific graph on these random variables. And now this has been completely abstract so far. Now to get a concrete model, to specify a concrete model, we need a few more ingredients. Because as said, this hypergraph only describes a family of distributions. And now to pick a particular member of this family, we need to also define the range of each random variable. So what values it can take. And finally, the compatibility functions, or equivalently, the potentials. Let's do that by way of example again. So for this Boykov-Jolly seeded segmentation, I had one random variable per pixel. Secondly, I defined this graph. Then thirdly, so the graph is what it looked like. Then I need to specify the range of the random variables. And each random variable can here be foreground or background, or call it 0, 1 if you prefer. And we have n of them. So taken together, this lives somewhere on a corner of a hypercube. And now talking about the potentials, this is where the Ising and the Potts model start to differ. Well, actually already for the range, because the Potts is multinomial, as we'll see in a moment. So in this model, I have single side potentials, where in the simplest case, I simply take gray value images as input, and then I say that at pixel number I, my potential for the state 0, I'm now calling foreground and background 1 and 0. So the potential for background would be given by the observation at pixel I. So OI is the observation. Here simply the gray value at pixel I. And the potential for foreground is 255 minus this intensity. So if you look back at the formula for what I called energy, there, you see that the energy was just a sum over these potentials. So if I want a low energy state, I want to find a low value for my potential. So what this here tells me is that I have high energy if a bright pixel is assigned to background, because 0 is background, and, well, the other thing is just the gray value. Okay, and vice versa, I obtain a high energy if I assign a dark pixel to foreground, and a low energy if I assign a bright pixel to foreground. So in these single side potentials, are for all unlabeled pixels. So this here is for unlabeled pixels. And for labeled pixels, because you saw that a user can supply labels, these red or these blue dots down there. For labeled pixels, I have psi I of 0, 0, and psi I of 1, something very large. If I is labeled as background, and vice versa, psi I of 0 is something very large, and psi I of 1 equals 0 if pixel I is labeled as foreground. And now comes a pairwise term. So psi ij of xi and xj is a parameter times difference of the absolute values of my labels times a term that looks if locally I have a large difference or not in gray values. So the first term here penalizes label changes, because if between two neighbors I and j, if they have the same label and this term is 0, if they have different labels then the term is 1. And then there is a factor here that modulates this penalty by looking at the intensity difference. So this is an image-dependent weighting term. If I plot intensity difference here, and here the weight of this penalty, then this looks like a Gaussian. So we are going to leave this penalty at its full value of 1 if I have two adjacent pixels I and j with no intensity difference at all. So intensity difference here would be 0. And if the intensity difference is large, then there will be almost no penalty in having a label change here. So that means my overall energy here is a sum of these single side terms plus a contribution from all neighbors. So I sum over I, and I sum over all pixels j, which are a neighbor of I. And for completeness, I should also write the gray value in the first term. And this is a single side potential. And or single side potentials. And this here is a sum over pairwise potentials. So this was compactly encoded by this picture we had up here. Single side potentials are not really shown in this graph. I could show them if I wanted, which will give you another famous image from, well, I'll leave it like that. Okay, so we have a very simple expression. So my overall probability, I'm just repeating the formula here, is that is all. So we have specified only these single side potentials and these pairwise potentials, and that has given me a model for an energy or a probability that depends on all pixels, or on all pixels and the labels for all these pixels. And we will see today that these trivial local potentials lead to not so trivial global models with some interesting behavior. So this is the Ising model. And also for concreteness, let's go through the Potts model. So this was the model for the stereo depth estimation. So we've specified the random variables. We've specified the graph, which looks perfectly the same. And here are the differences. So the range, this time the range of each of my random variables can be in a set from 0 to d. Or if I directly want to use these shifts, I could do something like from minus d to plus d or so. The point is we now no longer have 2 states per variable, but we have d plus 1 states per random variable. Then we need to specify the potentials. Again, we have a single side potential that simply well measures how good the match is between a patch from the left image and a patch from the right image. So single side potential at pixel I, and I'm now using L for a label here, would be some dissimilarity measure, like the sum of absolute deviation or the sum of squared deviations or whatever you like. of, on the one hand, the pixels in the patch on the left-hand side. So I'm writing left for the left observation, and let's say for brevity that this here is a vector, and this is the entire patch around pixel I. And then from the right image, I take a so let me change the label set here. Let's say this goes from -d up to +d, and I have easier indexing here. Let's say this is I minus L. So this would be the vectorized patch around pixel I plus L columns. So the sum of absolute deviations takes as input two patches. I take one patch from the left image and a patch shifted by L pixels from the right image. And the pairwise term, you can make these much fancier, but for now I'm just taking the following. So in other words, if the label is the same, then my penalty is 0. So this is a Kronecker delta here. And if my labels differ, then the penalty is given by theta. So if I'm plotting the contribution to the energy as a function of the depth difference, my labels here are discrete. So my depth difference can be 0, or it can be 1, or it can be 2. And for depth difference of 0, my penalty is 0. And for depth difference of 1, it's theta. And for depth difference of 2, it's still theta. And so on. If I wanted to draw this as a continuous function, then this is what it would look like, with a discontinuity here at 0. So in the Ising model, I had binary random variables. Here, if they have no ordering, if I consider them as categories, I can call these multinomial. And this would be the particular pairwise penalty that I've used here. And if you use a pairwise penalty like this, or one similar to that, then that's what you get out here, this result, which is much better than using only the unary terms. So the first result here is using only single site potentials. To use only pairwise potentials makes no sense because the image minimizing the pairwise potentials will just be an image of constant depth. But this here makes sense. This is the single site which couples you to the data, so the data term plus the pairwise terms that give you some smoothness. And if the single site potential is very sure, if one particular shift gives you much lower sum of absolute deviations than another one, then this can, depending on the choice of theta, this can overrule the pairwise terms. But if, let's say, there were two different depth values which gave you quite similar energy in terms of the single site potentials, and if the neighbors are of a more definite opinion, then the pairwise term can overrule, and well, will give you a smoother image like the one that you see here. So I've gone through these through these models in much detail to give you specific examples for what such modeling may look like. Again, the important thing is that we only need to define, we have a very sparse modeling. We only define local interactions. So this particular model here, it is, it has very few parameters. So using the sum of absolute deviations, okay, that's an arbitrary decision. But if you take that as given, or if you accept that, and if you also accept using this particular Potts potential here to penalize label differences, then you are left with this parameter theta here, which trades off the importance of the single site or data term versus the pairwise or smoothness term. So this is a parametric model, and for a given set of observations, so if I write down the probability of a labeling X in terms of the observations and in terms of the single parameter that I have, this has very few degrees of freedom compared with a full model. So if I made no assumptions whatsoever on a probabilistic model, I would get something extremely high dimensional. So even if conditioning on the observations, in the extreme case, I would specify the full probability table. So I would give just a huge list of what is the probability of having a certain assignment of labels to these random variables, and this would be number of labels at a single site to the power of n. And remember, so n here, for a megapixel image is 1,000,000. So that would be something completely unspecifiable, untractable, and so on. So we have a very, very sparse modeling here. That's the beauty of Markov random fields. So I first want to take questions, if you have any. Yeah. So you ask about inference. You ask how to find the lowest energy state or the most probable configuration of random variables. This is what I've politely glossed over, and this is what we will spend for these discrete Markov random fields that, like Ising the Potts model, what we will spend 2 weeks talking about. So there is a great abundance of algorithms of varying computational complexity and varying accuracy, that let you estimate these low energy states. A very simple one is, for example, iterated conditional modes, where you fix all random variables except one, and then ask for this one random variable, fixing all others, what would be the best label that I should give to this one? And then you iterate that over all pixels repeatedly, and that lets you end up in a local optimum. And then there are algorithms which also give you the global optimum, but they will be a lot more expensive. And how much more expensive depends on how precisely your interactions are defined, if they belong to a friendly or an unfriendly class. Okay, so after the break, I think I'll not talk about vector graphs today, but when we actually need them. And the rest of today, I want to talk about continuous valued Markov random fields. So here were the Ising and the Potts model that I've shown were two examples for discrete random fields. In the first case, the labels were allowed to be either 0 or 1. In the second case, they were minus maximum shift plus 1, and so on, up to plus the maximum allowed shift that you test for. These were two examples of discrete valued Markov random fields. And there has been, in recent years, a huge boost in performance of continuous valued MRFs. And this is what I will spend the rest of the day talking about after the break.